So some of you are from the first section are going to be joining us on this video. Sorry, I accidentally didn't record your 8 o'clock session. But that's okay. There's two alternatives. There's going to be this link to this one, and you can look back on the one that's labeled number 1 from a previous semester. So we don't have any material from, we don't have any assignments. By the way, let me get this out of the way. I still haven't graded your quizzes. I'm hoping to do that this afternoon. So I'm guessing that by tonight you should see something in the grade book. So this lesson, notice we skipped 2.1. Nothing wrong with 2.1. It simply talks about the difference between algebra and calculus, and we'll talk about it a little bit, but I didn't think it deserved a whole day, and it was the previous calc teacher. It wasn't in their curriculum either. So anyway, here we go. Chapter 2, lesson 2.2, the beginnings of calculus. And you can see the topic is finding limits, graphically and numerically. So actually, this is if you look on, I don't know, I think it's on the original schedule, you'll see that this was listed as a lab day, and that's basically what this is. It is a lab which allows you to discover limits kind of experientially. So by looking at charts and by looking at graphs, and that's what we're going to be doing today. Just a reminder that there is, if you go to the link for this lesson, you should see this website, and it's you'll see the same kind of thing is going on here that we're going to be doing today. You see how we have a chart here that we're looking at to try to discover patterns. Here again, a chart, and then we're going to be looking at the graph, the actual graph of the function, and we'll be able to try to find here we have a function with a hole in it. And anyway, we're going to be, it's the same kind of thing we're going to be doing today. Then there, if you click on the puzzle icon, just a reminder, that should bring you to more examples of the same. So you'll see what, I believe 3 more examples where you can look at more detail on the same concept that we're going to be going through today. Okay, so this is called in the schedule, Lab 1, Investigating Limits of Functions. You see how we have 3 things there? To try to get a feel for what limits are, an intuitive understanding. We're going to try to lay the groundwork for doing more rigorous study of limits, which is going to be coming in the days to come, and start to see in the third one there, experience the subtleties involved with numerical or graphical elimination of limits. So the examples I've picked, I think I've got something like 12 examples we're going to look at today. You'll see what I mean by the subtleties. You'll see slight differences in different kinds of functions. So let's get into it. So here's the first example. The function is x cubed minus 1 over x minus 1. And then what you see underneath it is me simply picking some values for x. And you can see there's, what do I have here? About 10 values for x. And I picked them in such a way, you notice how the ones with the red arrow next to them are all what? Just short of 2, 1.8, 1.9, 1.99, 1.999. You see how they're getting closer to 2? And then when you look at the blue, it's numbers above 2 coming back and getting closer to 2. So what we're doing is approaching 2 from both the lower end and the higher end. That's called the limit. So let me just write this down. So when you're so in terminology, we're finding the limit of this function as x approaches 2. That's some of the notation we're going to be using. So that's what this whole chart is set up to do. So do you see what happened to the function? Take a look in the chart. What happened in the red, next to the red, as x was getting closer and closer to 2, what is f of x approaching? You see how it's getting closer and closer to 7? 6.95, 6.995. You get the idea. It's getting closer and closer to 7. And how about on the bottom, when we were above and we were coming back, getting closer to the function? Do you see how, again, it's approaching 7? So it looks like, just from substituting a bunch of points, it looks like the limit of this thing, let me get my pen again, is I need to do that a little neater. Hang on a minute. We need to turn this thing and move it over a little bit. It looks like the limit of this function as x approaches 2 is 7. So let's go back and now let's take a look at the, so I'm going to uncover. So first of all, in the red, this is called a left-hand limit. Notice that 2 with that little negative sign up there as almost like an exponent. So this reads the limit of f of x from the left-hand side as x approaches 2 is 7, called the left-hand limit. And then in the blue, that's saying, hey, the limit as x approaches 2 from the right, that's a right-hand limit, and that's also 7. And the first thing we're going to learn about limits is when the left and the right-hand limits agree, then that is the limit. Notice I don't have any, on this one, I don't have any sign, but it just says the limit of f of x as x approaches 2. So when the left-hand limit and the right-hand limit agree, then the overall limit is that agreement, 7. Also, we also know how to find what's f at 2. Since x was approaching 2, what's f of 2? So if you just plain plug in 2, what do you get on top? 8 minus 1 is 7. 7 over 1, 7. So notice here, everything is in agreement. You got the left-hand limit is 2, the left-hand limit is 7, the right-hand limit is 7, the overall limit is 7, and the function value at 2 is 7. Okay, that's the simplest case, and we need to start adapting to that notation. Okay, let's take a look at our second example. This is actually the same function, but what's different here? Excuse me. Look in the table. So when you look in the table, you see how this time my x's are approaching what? Instead of 2, you see how it's getting closer to 1? Okay, and on the other side, we're approaching 1 too. Just a little bit above 1, we're approaching 1. Okay, so just from looking at this chart, what is the left-hand limit as x is approaching 1? So as we get 0.8, 0.9, now look at the f of x column. What's it getting closer to? 3. How about the right-hand limit? As x is approaching 1 from the right, 1.2, what's happening to these numbers over here? Uh-oh. Well, it still looks like it's approaching 3, even though at 1, you can't calculate it, right? Because you'd have a 0 in the denominator. Here, let's take a look at this function. So we'll take a look in Desmos. So here's I mean, this is a rather normal looking second degree equation. And here are the points as x is approaching, you know, this is 1 right here, and as x is approaching 1, it looks like the height, the intended height, would be 3 right here, 3. But what you can't see on this graph, and by the way, Desmos is really pretty good at this, but you can't tell it here, there's a hole in the graph at 3. Why? Because you can't substitute in 3. So the left-hand limit, 3. The right-hand limit, 3. Even though at 3 there's no value. Okay, so that's one thing that can happen. Now here we have a rather normal looking polynomial, x squared minus 4x plus 3. And as you can tell, I am trying to get x to be closer and closer to 2. You see how in the chart I picked 1.8, 1.9, and I kept getting closer to 2. As I was getting closer to 2, what was f of x getting closer to? You see how it's almost -1? And likewise, as you start a little bit above 2 and head back, where does it head? Looks like -1 in both cases. So the left-hand limit is -1. The right-hand limit, -1. They both agree, so the overall limit, -1. And in fact, what's f of 2? -1. So, anyway, it's perfectly okay. This is, again, a real normal looking function. And in fact, we know it's another parabola. And you can, as x is approaching 1, you can see all these points getting closer and closer to 1 down here. And, you know, that one's 1.8. That one's 2. Then 2.1. So you can see that those are basically a mimic of the points that we have in our chart here. This time, we don't have any undefined. There's no hole in this graph. Okay, let's take example 4. Number 4, we've got, yep, I can't erase this, that red ink is from something I can't erase. So anyway, it says the sine of 4x over x. Make that big so you can see what the function is there. Sine of 4x over x. Okay. And what am I doing with my chart? My x values are getting closer and closer to, see how they're getting closer to 0? And what happens to the function? Looks like it's getting closer to 4. Okay. How about the other way? When I try to put in positive numbers that are approaching 0, again, they seem to approach 4. Except for one thing. When I actually plug in 0, I can't calculate it. That's okay. You still got a limit. So the left-hand limit of this in the negatives is approaching 4. The right-hand limit also approaching 4. So therefore, the overall limit, 4. So remember, when the left and the right-hand limits agree, that's your overall limit. Even though, in this case, the actual value at when x is 0 is nothing. It's undefined. Let's take a look at that graphically. This is a kind of an interesting looking function here, and you can see that as we're getting, so we're picking points like -0.1, and you can see at that time the y-coordinate is 3.894. Then over here we got positive 0.1, and then here, of course, we actually have positive at 0.01, and you can see we're getting closer and closer to 4. So that the limit of this truly is 4. Even though at 0, you cannot divide by 0. So there's a hole, even though you can't see it, right up there at the apex. Do we have a limit? You bet. Why? Because the left-hand limit and the right-hand limit agree. Okay, let's look at example 5. So this is kind of unusual. Now, because I'm using the formulas on the left are Desmos formulas, that's the way you write absolute value on Desmos. So, you know, bar is around 5x. The absolute value of 5x divided by x. Once again, divided by x, you know that x cannot be 0. And if you look, isn't that where the table is headed? Getting smaller and smaller negatively until it gets to 0. And then positively, same thing. Positively, tinier and tinier to 0. Now, what happens? When x is approaching 0 on the negative side, you notice how all the answers are stuck at -5? -5, -5, -5, -5. On the positive side, when x is approaching 0, everything is +5. And as you know, you can't plug in 0. So on the left-hand limit is -5. The right-hand limit is +5. Notice those two do not agree. And so we say the overall limit of the function as x approaches 0 does not exist. And we use this abbreviation DNE. So when the left and the right-hand limits don't agree, you don't have a limit overall. It does not exist. And of course, you can't plug in 0. Now look at what happens on this when you look at the graph. Excuse me. I'll make it smaller so we can see the whole thing. So you can see here that when x is approaching 0 from the left, you see how we're stuck down here at -5. But when you take the limit as x is approaching 0 from the positive end, we get a +5. And you can obviously see they whiff. They miss each other. The left and the right do not meet. That means the limit is D and does not exist. Anybody, I don't know, it's all I've done is yap so far. Does anybody have any questions so far? Let's look at another one. Example 6. So this is different. You see how this time our function is 1 plus x over 2 raised to the 1 over x power. And you can tell, again, I'm going for what? X approaching 0. So I did it first on the negative side. Negatively, we're getting closer to 0. Looks like we're approaching, you know, this 1.64 thing. And when x is approaching 0 on the positive side, again, it seems like we're approaching something about 1.65. Okay, so what's going on here? Well, the left-hand limit appears to be 1.6487. The right-hand limit appears to be the same. Therefore, the overall limit is that number, 1.648. I didn't put all the digits down, but now when you actually make x 0, why is this 0? Well, because the exponent here was 1 over x, and if you make x 0, that exponent becomes garbage. It's 1 over 0, and that's why it's undefined. Now let's take a look at that one on decimal. So as x is approaching 0 from the left, you see it's decreasing, and it looks like here's that 1.648 right here. Okay, and as x is approaching it from the right, it's again at that 1 point, it's that same number. That's where it's headed to. But we know that at f of 0, it's undefined, so there's a hole in the graph. But still, do the left and the right-hand limit, are they aiming at each other? Even though there's a hole in the middle? Yes. So therefore, we do have the limit of this function as 1.648. So even when there's a hole in the graph, if both sides are from left and right are coming at each other, we have a limit there. All right, example 7. Well, you can see we have another division by 0 possibility because we have sine of 4x on top. We have x squared on the bottom. We all know that x can't be 0. And in fact, look at the chart. As x is getting closer to 0, what's happening to the f of x? What's it at there? Negative 400,000 when x is 0.0001? Yeah, negative 400,000. So it's a huge negative number. What's happening as x approaches 0 from the right? Getting massively huge, positive 400,000. So, by the way, I mean, I could have even picked smaller numbers like negative point. We could have even gotten tinier without getting to 0. So what's going on here is the left-hand limit as x is negative at approaching 0 is actually negative infinity. That's where it's headed. And the right-hand limit is the opposite, positive infinity. Notice these two left and right-hand limits do not agree. So we would say the limit of the overall function does not exist. Let's take a look. Yeah, and you can see as x is approaching from the left, what happens? It's going down big time, and you're getting these, as you get down here, these numbers are getting really tiny. I know I've only got -7, but I mean, we could go way down here, -22. We're already at -21 for a y-coordinate. Here, -0.1, we're at -40 already. And of course, the farther we go down, the more it approaches negative infinity. And the opposite happens when you approach 0 from the right. Positive infinity. Do they ever meet? No. No limit. Example 8. Okay, back to a good old polynomial, x squared plus x minus 1 over x minus 3. And you can see, of course, we have a denominator, so what can x not be? 3. So let's find the limit as x approaches 3. So you can see I did the positives on the top. If it's approaching 3, I'm sorry, I did the from the left side, 2.9, so from less than 3, we're getting closer to 3. And look what we get, negative 109,993. So a huge negative number. As we're approaching 3 from the right, I again have what? 1.1 times 10 to the 6. So in other words, I have another huge number, but this one's positive. This means 1.1, move the decimal 6 places to the right. So this is just as big, only positive. So you can see we have a big negative, we have a big positive, two don't meet. The left-hand limit would be again regarded as negative infinity. The right-hand limit, positive infinity. They don't agree, so it does not exist. And when you plug in 3, you get garbage because of division by 0. So make this a little smaller. Yeah, so that you can see on the left side, as you get closer to 3 from the left, this thing is dipping forever downward, negative infinity. On the right side, as you're getting closer to 3 from the right, this thing is getting huge. As we get real close to 3 here, it's going way up, positive infinity. They'll never meet. Okay. Questions? Again, anyone? I'm looking over. I also have to check my chat because some people might choose. You can type your question in too. Okay, number 9, example number 9. So again, kind of a classic. We got x in the denominator. You know that x can't be 0. Well, what happens with the limit as you get close to 0? So on the top, I'm approaching from the left. -1, -0.1, -0.01, -0.001, -0.0001. And what's happening to the function? Negative huge. And on the right, what if you approach 0 from the right? You get a positive huge. So this is very similar. The left-hand limit, negative infinity. Right-hand limit, positive infinity. Therefore, no limit does not exist. And you can't, when you substitute in 0, you get trash, you get undefined. Graph. You can see how those two curves never will meet. They never meet on left and right side, and that's the reason for the D and E does not exist. Example 10. Now, we got a little bit of a problem here. So when you use Desmos, you remember what a function, a piecewise function looks like, where you have parentheses like this, and you divide it into 3 parts. So this says, use this formula when x is less than 1, use this formula when x is 1, and when x is greater than 1, then use the bottom formula. That's called a piecewise function. This happens to be how you type that into Desmos. We'll talk about the technical aspects of that, but anyway, not right now. This is what that is. Okay, so this is a piecewise. So the question is, what's going to happen as x approaches 1? Well, as x gets closer and closer to 1, you see how it looks like we're getting what? The answer is getting closer to 6, 5.998. As x is getting closer to 1 from the right side, it also seems to be getting down closer and closer to 6. So it looks like the left-hand limit is 6, the right-hand limit is 6. So left-hand limit, 6. Right-hand limit, 6. What does that tell you about the overall limit? 6. Now, there's one surprise left here. What happens when you plug in f of 1? You don't get it. That's okay. I'm going to show you, so we're going to take a look at the graph here, what's going on. So here are the two, this is actually the function in pieces. You got, as x is approaching 1 from the left, you've got this curve coming up. And this is x is approaching 1 from the right. And then here, right here, is what happens at 1. Because the two parts of the curve still connect, they still point at each other, this is a legitimate limit, even though the function right at that point is separate and up above. So again, the idea is you got to have the left side meet up with the right side, and even when there's a hole in the graph, you can't see it, I know, but I can't show you that point, but when you're right at 1, you have a hole in the graph. And so, that's okay, it's filled up here, but the two sides of the graph still agree. They hook up left and right. So we have a function, we have a legitimate limit. All right. One more example. I want to take a look at example 3. This is, again, a piecewise function. And so when x is less than or equal to 3, then use this formula. And when x is greater than 3, use this formula. So this is a piecewise function. I'll just show you what it looks like. We'll come back and look at the chart afterwards. Okay. So as x is approaching 1, we've got this part of the parabola, and as x is greater than 1, it was 1, right? Yeah. As x is approaching 1 from the right, you've got this thing up to, up to right near where I just pointed at that point. You see, they connect. They connect. And so let's just go back and look at the chart now. So our agreement on the chart is the left-hand limit seems to be approaching 15. The right-hand limit is 15. Therefore, the overall limit is 15. And here, everything's in perfect agreement. So you can see there's quite a few different scenarios. So let's go over the basics here. When the left and the right-hand limits do not agree, you don't have a limit overall. When they do agree, bingo, you got a limit. Now, even when you have a limit, that may not equal the actual point of the function. Here, in this case, it does. But I mean, you've seen many times where there was a hole in the graph. As long as the left and the right-hand limits agree, you've got a limit. Okay. Now, first of all, let me show you what the assignment looks like. I think you already know, but so for 2.2, these are the problems you're supposed to work on. We'll take a look at a few of them, and we'll just discuss. And the whole idea is you're supposed to get into these tables. You're going to have to do tables like I did, and you're going to have to look at graphs. I encourage you to either use your graphics calculator or Desmos to help you with the graphing. So let's make that a little bit smaller. Wow, where am I? Okay, this is 2.2. Let's go to 2.3 and back up. So when you start looking at these problems, you see how they have tables there? That's pretty much what I was showing you on the left side of all of my examples. So take a calculator and crank them out. Plug in, what happens when you plug in 3.9 for x? Get your function and put it here in the f of x category. Then do the same. And then, so you got 6 of those to crank out. Where are they both heading at? From the left and the right, are they heading in the same place? Then go ahead and do your graph and see if that agrees. And so what's the bottom line here? You're supposed to come up with an estimate for the limit from looking at the table and looking at the graph. Now, I know you're probably thinking, what's his estimate, baloney? But we're just trying to give you an intuitive feel for what a limit is like. Okay? So this really is, this is a good exercise. All right, a little bit later, you're going to get in, you're going to be given a graph. Like, take a look at number 19 now on the assignment. Again, it's, what do we call that? A piecewise function. One graph on the left, another graph on the right. And notice there's a dot. F of 0 is, so except for 2, this is a straight line. But at 2, it's this point down here on the bottom, this 0. What's the limit of this as x is approaching 2? So if you're coming from 2 from the left, it seems to be, I'm going to ask you guys to respond here verbally, please. As this graph goes from left to right, when you get to x equals 2, what is y looking like it should be?
Well, there's a hole in the graph, so the actual y value is 0, but the y value at that point where the hole is 2.
So it's heading toward the hole, right?
Yes.
Yeah, so that's the limit. So in other words, as x is approaching 2, it looks like the function is approaching 2. Is that true from the right too?
Yes.
And so because the left and the right hand limits agree, this limit as up here is equal to 2, even though f of 2, like you pointed out, is 0. So the limit of this one is 2. Look at number 20. Here again, we have a hole. We have this double. We have a graph with a hole in it with a point off. Where, as you look at, as x is approaching 1 from the left, where does it look like the y coordinate is heading? Somebody else, please. So as you move on this graph from left to right, where is it heading when you get to x equals 1?
4, 3.
Looks like 4, right?
Yeah.
Yep. And how about from the right? Again, it's heading for 4. So what's the limit of this function as x is approaching 1? It's all heading at 4. So that would be, okay. I'm just going to look down here at number 8, estimating a limit numerically. So use a graphing utility to graph the function and confirm your result. So how about this one here? Let's number 8. We have x plus 4 over x squared plus 9x plus 20. And we want to know the limit as x is approaching -4. Okay, so let's do the graph. Let's see. Guess we gotta. Let's do a new Desmos here. Okay, so we have x plus 4, and that's divided by x squared plus 9x plus 20. Okay, so what's the limit as x approaches -4? Again, let's get a volunteer and somebody else, please. So as you move from left and right, what does it appear the height we are approaching when x is -4?
1.
Yep, it's 1. So this is all looking at tables and looking at graphs and knowing that as long as the left and the right hand limits agree, we can do this thing called a limit. So a limit is a mathematical way of saying, where is that thing headed? That's pretty much what it comes down to. So you got your assignment here. We're going to be doing a lot more with limits, but this is a good beginning. You need to get into this, get a feel for these limits. And limit is a very important concept in the beginning of calculus, where we're headed shortly. Does anyone have any questions you'd like to ask? Okay, not seeing any. Thank you for joining me. I hope you have a great day. Enjoy the sunshine. Thank you.